laser industry specifically.
It has changed dramatically.
The field of biophotonics was just getting started.
The first instrument that I bought was a microwave spectrum analyzer.
It's time to shed light on our universe. This is All Things Photonics, a podcast about the physical science of light. Join us as we explore the latest in lasers, optics, spectroscopy, and microscopy. Each episode, you'll hear from leading voices from across the photonics landscape. We're brought to you by Photonics Media.
This is Associate Editor Joel Williams. Here are this week's top stories. With the observation of high-energy multidimensional solitary states, INRS researchers have pushed the boundaries of high-energy laser pulse propagation, allowing the direct generation of extremely short and intense laser pulses, which are highly stable in time and space. The team believes the research will enable the development of compact, high-power laser systems with a wide variety of industrial applications, including micromachining and material processing. A team of researchers from the University of Vienna has observed the successful formation and interaction of highly ionized krypton plasma using femtosecond coherent ultraviolet light and a novel four-dimensional model. The research may ultimately deliver insight into the physical formation of the universe. A technique called SPOT, which stands for Spectrum and Polarization Optical Tomography, is providing researchers with a, quote, street view of lipid membranes surrounding cell organelles, thereby allowing insight into lipid dynamics. The work is the result of a collaboration between Peking University and the University of Technology Sydney's Southern University of Science and Technology Joint Research Center for Biomedical Materials and Devices. George Washington University researchers have combined multiple transverse coupled cavities to develop a new vertical cavity surface emitting laser. The cavities in the laser system enhance the laser's optical feedback capabilities, helping the laser demonstrate record-fast temporal bandwidth, the researchers reported. And finally, scientists from NUST MISIS Technological Initiative Center are developing a prototype of an infrared photon video detector. The camera, believed to be the first of its kind, will have applications in secure communications, including satellite, quantum computing, and diagnostic medicine. The Ministry of Industry and Trade of the Russian Federation is carrying out the work via contract. Coming up, Imperial College London provost and chair in experimental physics Ian Walmsley joins Jake Saltzman as our featured guest this week on All Things Photonics. I'm Joel Williams, and you're listening to All Things Photonics.
Today's episode is sponsored by Coherent. Coherent lasers have been enabling breakthroughs in scientific research, life sciences, microelectronics, and materials processing for over 50 years. Today, we're introducing Coherent Amplify, a series of virtual events. Join us for the inaugural conference on December 10th, focusing on neuroscience and cell biology. Don't miss out on world-class keynotes, session talks, roundtable discussions, and networking opportunities. Register today. Learn more at www.coherent.com/amplify. Join us in January for the inaugural Photonics Spectra Conference. 4 days of online presentations spanning lasers, spectroscopy, optics, and biomedical imaging. 60 presenters all in one place, focusing on the latest in applications, trends, and advancements. Registration is free. January 19th through the 22nd, right here with Photonics Media. Visit photonics.com/pscinfo for event details.
We're joined today on All Things Photonics by Ian Walmsley. Ian is an elected fellow of the esteemed Royal Society and a leading contributor to innovation in quantum and ultrafast optics, as well as optical metrology. He serves as a fellow of the Institute of Physics, and from that organization was honored with the 2011 Young Medal and Prize for his contributions to optical physics. He is provost and chair of experimental physics of Imperial College London. Hello, Ian.
Hello, Jake.
I want to start with a question that stems from a plenary address that you gave a couple of years ago. In your plenary at the 2018 IEEE Photonics conference, you identified some of the near-term uses, potential uses for quantum computing, and one of them was to establish simulations of quantum structures that were already known. What are some additional near-term quantum applications that you may be able to identify for us?
There are broadly two that could be seen to be quite near-term, I think. One is around simulations, and the other is around optimizations. So in simulations, the idea that you can analyze and design molecules or materials that have clear quantum properties, and that's basically all of them, is something that I think is one of the early promises. And that could occur in a number of ways. One is direct simulation, if you like, so building a sort of analog version of the system. And a second is to utilize a limited capacity specialized processor, so it's an error correction, perhaps, which performs particular tasks in sections of an algorithm, so a sort of hybrid quantum high-performance computer. And some of that work has already shown the ability to do materials analysis that is really quite powerful. That approach, too, I think, is more generalizable. So it's possible that new approaches to solving partial differential equations will be possible, and that has then a very broad range of applications to fluid flow or what have you. So that's the sort of simulation side of it. Optimizations really based around search problems, which can range anything from things like looking for the ground state energy of complex molecules or materials to logistics problems and solving routing challenges for process flow or manufacturing or delivery, for instance. So, no, if a quantum computer allows you to get your Amazon packages just that little bit quicker, we'll all be better off.
One of the phrases, I suppose, that I've heard you use on more than one occasion are aimed to demonstrate a clear and usable quantum advantage, one that is not only evident and apparent, but also has application. So I want to take a step back and ask you, what have been some of the breakthrough or seminal moments in the recent past that have driven us towards that clear, usable quantum advantage?
I would sort of point to work that's broadly spread over the past 30 or even 40 years, where a number of key steps have unlocked the potential of this area and shown how significant barriers can be reduced. So clearly there's the original concept, which often is attributed to Richard Feynman in the early 80s. I think then two sort of parallel streams. One is the demonstration that there existed algorithms which had a palpable advantage when you ran them on a quantum machine. And from the early Deutsch algorithm to Shor algorithm, some of the more modern ones around equation solvers and what have you. The other strand was really how to harness entanglement in a way that gave you clear technological advantages. And that's been most prevalent in the early stages through communications, so secure communications through the ECHA-92 protocol, for example, and in quantum sensing, the ability of quantum states to provide precision in sensors that you can't get any other way. I think the next big step was the first challenge to scaling. Why don't you see big quantum states in the world? And the big breakthrough there was quantum error correction from Andy Steen and Peter Shor and Calderbank and others. So those were the key early things which showed that physics allowed you to build these machines and to deliver some potentially useful applications. And a lot since then has been around making the hardware, doing the hardware engineering that really showed that this was feasible. And so the steps like the Google and IBM and other machines in superconducting or the ion traps or the ion trap networks have all been sort of breakthroughs in engineering that have really enabled external application communities to start thinking about broad real-world applications.
When you talk from moving from sort of these more fundamental measures to things like error correction and ultimately application, it seems like we aren't off when we talk about, people like myself talk about quantum technology being on the cutting edge. What are some of the next steps to sort of put us, if not over the edge, bring us right to the edge?
The clear challenge now is scale. If you take a state-of-the-art supercomputer, you can do a simulation, a full simulation of a system with a few tens of qubits, maybe 40 to 50, and that's state-of-the-art. So if you can build a small quantum machine which has that capability, you can already step beyond what state-of-the-art supercomputers can do. And that's certainly the regime of quantum advantage that a number of people are shooting for. And you'll remember the Google paper from last year in Nature, where there was an example of an algorithm that had been done in a way that by some measures could not be replicated in a conventional computer. That continual quest is one. But the next step, I think, is really showing fault tolerance in a machine and architecture which is palpably scalable, so all of the elements meet the threshold for being able to build a bigger machine on an engineering platform that you can actually build in a larger way. You know, I would say that at the moment there are no known physics barriers to this machine being built, but there are some pretty fierce engineering challenges.
As someone who's been in quantum and sort of the realm for an extended period of time, are you pleased with the progression, the state of things now, as opposed to what they were 30 years ago or perhaps even longer?
Yeah, I think it's an exciting time now, but it was exciting 20, 30 years ago too, but just in a different axis. And I think it's an interesting narrative as to how this arises. It arises from some very basic considerations of science and new areas of discovery, people thinking outside the box in a completely orthogonal direction. And then as the barriers fall, moving into a place where people can see advantage from applications. So very different sort of audience, very different sort of milieu in which the research is now done. But in all ways, very, very exciting.
And to be sure, the fundamental science has not gone by the wayside. Not only has it remained in education, it's remained at the forefront of industry in many ways. I want to ask you, especially given the exciting possibilities of quantum science, with regards to physics and optics in particular, how are those things now being taught, given the evolution of quantum?
I think that they are taught in a way that is much more application-oriented, in the sense that there remains a sort of fundamental piece. You have to understand what waves are. You have to understand wave-particle duality. So you have to know about those things. But it's much more compelling, I think, for people to see, here is a particular task you're interested in, and here's how our knowledge from these areas helps us solve that problem. And an advantage of doing that is that you can reach into many, many fields with photonics, for instance. Everything from materials processing to biosensing to telecommunications to quantum computing. And the fact that it's such a ubiquitous medium, light is such a ubiquitous medium, I think gives it an excitement that's unparalleled. Certainly I'd want to study it again.
And you perhaps have I hesitate to use the word unique, but you have I suppose, distinct perspective from your position with Imperial College London. And I want to talk about that, and I plan to here in a moment. But first, I want to ask you about the quantum domain. And given its nature and that it's progressing today, it's comprised heavily, dare I say prominently, of young companies, startup companies. From the science side, what's it like to work in such a domain?
It's a different way of working than even 10 years ago. That is, I think, students and young colleagues who who start off with PhDs and postdocs certainly can see that there are opportunities now in industry in a way that they can help drive and set the agenda. And I think that's a very exciting thing for them and for the community. And I think a key point for quantum technologies is that many of them are in a position where doing the engineering is the key to getting the next step in the technology, advancing the technology. And I think industry is just a better place to do that. The structures, the way in which work is done, and the sort of scheduling is very different than a discovery-based field. It's great to be able to work alongside such companies, both benefiting from the skills that they have and enabling ideas to feed in, because it's still a domain where new ideas can have a fairly immediate impact. So it's different than it was 20 years ago, but great, very exciting still.
Sure. We're speaking with Ian Walmsley, who is provost of Imperial College London, and I apologize for cutting you off there. I was just so excited to ask you a contrast question. You spoke just now about young and startup companies in industry in the quantum space. How does that differ, if it does differ, from the photonics industry, in the photonics space?
I've not worked in a photonics company, so you'll have to forgive that some of this is probably not a full and proper perspective. But I think photonics companies often tend to be sort of component companies rather than systems companies. And I think the quantum companies are really, at the moment, a lot of the startups are thinking of themselves as system companies, so that the platforms they are developing are not just components to sell into other systems, but they are trying to use those to bootstrap up a system itself. That, I think, is perhaps one of the differences. Of course, photonics industry is much more mature, and that also means that you've got to have a significant step to be able to deliver a new product that's displacing something already in the system. Whereas the quantum domain is still pretty open, and I would say it's not even determined which is the final optimal platform for a quantum computer. So that openness, I think, gives a great deal of flexibility.
You speak of the quantum domain, and one of the interesting things about you is that you come at it from multiple different angles and perspectives, including from industry. And one of the young firms in the quantum space is one to which you're personally connected. Can you tell us a little bit about Orca, ORCA, and its mission?
Yeah, Orca Computing, I'm a co-founder of, together with three colleagues, Josh Nunn, who worked with me in Oxford, and he and I are sort of the technical piece of it, if you like. That came out of work that we had done together around photonic quantum memories and patents that arose around that. So that provides a means for us to think about a photonic-based computing platform that derives its power from a sort of the ability to build a repeater, to mitigate some of the probabilities associated with quantum operations, for instance, and therefore to harness the capabilities and components of the telecoms industry to interface with that, and that would build us a platform where one could get to a simulator and to a quantum computer in the longer term. And we were fortunate to pair up to industry and startup people who had a great deal of experience in running companies, and therefore it was a match that worked well for us. So it's a great little company, has a really fantastic team. Of course, I would say that, wouldn't I? But really plugged into the UK national program and off and running. So it's great to be part of. And of course, it's one of only a large number of such companies around the world, but indeed about half a dozen in the UK. And I think the UK national program has really helped seed that agenda so that new companies can get up and running. And I'm hopeful that among those companies will be some of the leaders of the future in this space.
Tell us a little bit about the UK national program and its stance towards quantum and quantum innovation.
The UK program has been running for about 6 years now. It's essentially a sort of decade-long program now in its second phase. And it started really with a vision that the time was right to take the great science that had been done in advancing quantum information processing over the past 20 years and to really help the UK build an industry sector which could be a leading player in the global quantum information processing technology space. And to do that, it, I think, constructed quite a good program around research and development hubs, which built the technology in 4 domains: sensing, imaging, communications, and computing and simulation, together with an industry program which helped companies interface with those hubs and build their own sort of supply chain models, as well as a strong entrepreneurial and technology training for students and postdocs, so building a skills base that could help support that technology sector. And the second phase, starting a year ago, builds on that in a more focused way. So now, for example, it added on a national center for quantum computing, where the aim is to be able to both push along some of the engineering challenges, which are perhaps at an too early a stage for some of the bigger companies to invest in, to build an application space, and really to be able to put the UK in a position to have a functioning quantum computer in the due course so that it continues to play a leading role in applications around the world.
To that point of industry and entrepreneurship and skill building, it often feels that the industry tie-in is almost the last to occur for end users, practitioners, and experts. And now that you have that with Orca and through your involvement with the UK's national strategy, your connection to the science is really multi-sectored, certainly a strong research perspective and certainly an educational perspective. I'm curious how those multiple angles of access fortify or shape your perspective of the current state of the science.
Science and technology are in a real pole position. And not just with respect to quantum, of course. It's clear that technology is going to be driving society and driving the economy, just as it has been over the past few decades. And the rate of advance is pretty rapid. The sort of alignment of both discovery and skills on the one end through technology development and then to applications and users, I think is joined up in a very positive way around quantum. And I think as a general proposition, we see that across a number of different sectors. So I think there is an increasing appreciation in universities of the value and ways of working with industry, an increasing perception in industry of the value of connections to universities, an understanding in government that helping support that symbiosis is going to be good for society in the long run. So I hope that we can together build lots more opportunities for lots more people. That's really a goal.
In your position with Imperial College London, the provostship, you work closely with these up-and-coming minds from, as you say, across disciplines in science and technology. What are some of the core values you and the institution attempt to impart on this next generation that is really poised, I suppose, to deliver scientific innovation?
Well, I think the ones that you would expect, I hope: creative independence, integrity, engagement and partnership, and entrepreneurialism. So the sorts of things that allow you both to work independently and work productively across teams of any scale, being open and identifying the partners that you will need to deliver significant outcomes. So be ambitious at the same time. Those are the kinds of things and the kind of milieu that we want to be educating students in these days, and interfacing with industry to enable them to take on some of the big challenges out there.
With these advances that we've spoken of today in ultrafast optics, photonics, and certainly quantum, one has to think that higher education, be it in attitude or be it in curricula, is changing a little bit. Is that fair to say? And if so, how is higher education changing or at least adapting to produce this next generation of these highly skilled scientists and engineers?
Clearly, a major change, and accelerated over the past 6 months, is the ability to reach wider geographies and wider demographies using digital and remote learning. And that, I think, is a change that's going to accelerate. But there are two elements that I think places like Imperial and other institutions will have too, and that is having students be able to engage with people who are really setting the agenda on knowledge and its application. Education is not a commodity. It's really learning is something that you do in engaging with others, and working with the people at the cutting edge of their fields is a way to, I think, really both inspire and motivate and impress people as to the sorts of impact that they can have. So that engagement is one. The second is that some skills are very practical. You still need to be in a laboratory trying things out in order to build those skills. So I think there's always going to be an element of that involved in any leading educational institution. Those are practical pieces, but you're absolutely right that providing a context in which education is done and additional skills, our enterprise lab at Imperial supporting students building their own startups and understanding how their ideas can be framed and turned into something real is an additional piece of work that probably wouldn't have happened 25 years ago.
Speaking today with Ian Walmsley, joining us from Imperial College London, of which he serves as provost. Ian is also the 2011 Young Medal and Prize winner for his contributions to optical physics. And I want to ask you a question that takes you back a little bit. As a student or a member of faculty, an administrator, advisory team member, and in other capacities, you have been a member of some highly recognizable and prestigious communities on the optics and photonics spaces. University of Rochester, University of Oxford, Cornell, Max Planck Institute for Quantum Optics Science Advisory Board. Can you compare and contrast some of those different environments and speak a little bit to how each environment has combined to steer you towards the accomplishments that you've now racked up?
You're right. I've been extremely fortunate to have had the opportunities to be at those institutions, and it's great. I couldn't have asked for a better path to follow. I think they all bring different characteristics, whether that's a particularly close-knit community with a long history. The Institute of Optics at the University of Rochester had some towering figures in the field and had combined basic and applied research in photonics in just an unprecedented way. A place like Oxford has just a great deal of freedom and a great deal of brilliant people passing through all the time. So the ability to discuss and generate new ideas was just marvelous. Each of them has their own characteristics, and I think one learns something different, both in the way they go about it and from the people who you meet. But it's really the latter. It's really the people who you interact with who shape things the most, I think. And I've been very fortunate to have some fantastic teachers and mentors and colleagues and students and postdocs. So that's been really great.
We've worked our way now into a conversation really about education, and one of the things about education is it doesn't happen without teaching. The learning does not commence without the teaching, and certainly teaching is something that you've done in your career, and I'm curious how that's contributed to the research.
Yeah, well, as we were saying earlier, learning is really about engagement, not just about knowledge itself. So it's about how you think about things. It's about how you approach problems. It's about what questions you think are going to be important, as well as the technical skills in mathematics or engineering or physics or whatever it is that you need to know. So for me, engaging in teaching in that way was really fruitful. And to be specific on your question, how has it contributed to research? I think there are two ways. First of all, you have to answer questions from smart people who are thinking about things perhaps for the first time. So they always bring a different perspective than the one you have developed yourself. And that's extremely valuable. So asking a question in a new way opens up new lines of thought that you might not have triggered in any other way. So interacting with students, understanding their questions, figuring out how to answer and respond in ways that are meaningful for them is really a fruitful way to get your ideas moving. Then I think there's the more specific. I'd say that one of the most successful patents that I ended up having grew out of the very first teaching assignment I had at Rochester, where I was teaching a subject that I didn't know very well. I had to learn, and in learning, that helped me with ideas that I could apply elsewhere in my research. So very directly, I can trace that patent back to some ideas that I was teaching in that course. So those are two ways.
I have to ask, what's the patent, and perhaps the bigger question, what was the technology, the research, the innovation that led to it?
So the patent was for a method to measure very short pulses of light. How do you, if you've got a pulse which is a 10 femtoseconds in duration, that's about 10 million billionths of a second in duration, so really short. You've got no detector that could possibly respond that fast, and no oscilloscope that could display it even if it could. So how do you know how long that pulse is? And indeed, how do you know what the shape of that pulse of light is? We worked on that in the 1990s and developed a method which goes by the name SPIDER, which is spectral phase interferometry for direct electric field reconstruction. That was a trend at the time. You have to have an acronym. But the spectral phase interferometry was really derived from a course I had taught on optical testing and evaluation for imaging systems early in my career at Rochester. So yeah, that was a lineage that worked out quite well.
Do you find yourself in these moments of reflection? Not that was one necessarily, but you've now, as I mentioned earlier, you sort of touch all the bases in your access to the science, and in particular to quantum. Do you find yourself reflecting back on some of these trends and ideas that may have been mainstream in the 90s and maybe pinch yourself in realizing that, those have enabled quite a vast road of discovery here as we enter 2021?
It's always the case, I think, that there are many, many ideas contributed by many people that all go into advancing the field. In some ways, you're right. It's nice to think, something that one has contributed oneself has enabled something to go forward. But I think everybody who's a researcher would know that there are also many ideas that you had that you thought at the time were really important that turned out not to be so important. And I think that's just the nature of it. You have to think as to what is the most ambitious and what is the most impactful thing that you could do, whether that's about new discovery or new application. And you work hard at that, but many times it doesn't go anywhere. And sometimes when you're not expecting it, it goes somewhere quite powerful. But the great thing about having institutions like universities is that it's a place you can take those risks and be creative and help contribute to how science advances. So it's a great privilege in that sense.
So with that, I'll put you on the spot with quantum optics. What are some of the trends, the discoveries, the pursuits that ought to be on our radar looking into the 2020s?
I expect that you will continue to see, around quantum in particular, a proliferation of the technologies and a refining of those in ways that are going to be unexpected. For example, an old idea in quantum sensing, back to Carl Caves in the 1980s, has now been implemented on LIGO, and that's allowed an order of magnitude more volume of the universe to be searched for gravity waves. So I think that's the kind of thing that we'll see more and more of, and I think that's really exciting. Again, it's optics as an enabling technology for new discovery and new applications. I think we will not see a let-up of the pursuit for quantum computers, and my own belief is that photonics will have a role to play in that one way or another, because light has the ability to encode and transmit quantum information in ambient conditions. And that's a unique feature of that medium. So I think that those trends will certainly continue. And I think one will see optics continue to play a really central role in a wide range of fields, as you see now, only expanded. Optics is still the place to be, even though it's a 400-year-old discipline.
We've been speaking today with Ian Walmsley, joining us from London. He is provost of Imperial College London, the 2011 Young Medal and Prize winner, a fellow of the Institute of Optics, and an elected fellow of the esteemed Royal Society. Thank you for joining us.
Thank you, Jake. It's been a pleasure.
Researchers at the University of Luxembourg have demonstrated a new method for generating well-controlled structural colors. Unlike dyes, structural colors rely on the use of transparent materials to generate a spectrum of colors. The research here, that we'll discuss in a moment, generated green, blue, and red using what are known as liquid marbles and cellulose-based polymers. The researchers' system relies on a cholesteric liquid crystalline self-assembly process, and it responded well to noticeable environmental changes. The work ultimately improves on previous work that necessitated time-consuming sample manipulation. The advance establishes a precise and yet straightforward possibility for tailoring structural colors. The advance also establishes new possibilities for use not only with soft photonic elements, but also with biobased sensors. Here to unpack all of this from the University of Luxembourg is Dr. Manos Anyfantakis from the university's Experimental Soft Matter Physics Group, part of the university's Department of Physics and Materials Science.
Thank you for the invitation. I'm very happy to be with you, and I look forward to our discussion.
So the work we just described involves two terms that I'd like you to break down for us, if you could. We'll start with structural colors. What are we talking about with that term?
So let me first start by describing in simple terms how color is produced that we see. So when we have a material that is illuminated with white light, which we know contains many wavelengths, then in order to see color, it means that some of the wavelengths that we send in, they come back to our eyes, and some others are, so to say, eliminated. And the question now is how this elimination process, if I would say, works. So there are two ways. In the first, the most common way, what is happening is that we have exchange of energy between the wave and the material. So some of the photon energy is absorbed by the material, and then the electrons, they can go to higher states. Therefore, it means that we have consumption of energy. This is the way that pigmentary colors work, and this is what we know. This is the common way of coloration. That's what we see, for example, in metals, in pigments, and dyes. Now, there is a second way as well for eliminating some of the wavelengths that we send in, so they don't come back to us by reflection, for example. And this involves a structure within the material. So now we have a material that's completely transparent, so there is no energy absorption, so no photon energy exchange between the wave and the medium. But what happens, there are other phenomena like reflection, refraction, interference, for example, that are responsible for eliminating some of the wavelengths that they don't reach our eyes. And then what we see, so the rest of the wavelengths, is the structural color. Now, this is interesting because, of course, it's encountered a lot in nature, but also we can learn a lot about the interaction between the light and the nanostructures in the material, which can be quite complicated. And from the practical point of view, structural colors are interesting because they are resistant to fading. I was reading an article a few days ago, and there was a picture from a fossil of an insect that is like 40 million years old or something like that, and it still reflects strong blue light. So I think that's something quite interesting.
Yeah, and the other term we mentioned in our intro was liquid marbles as being pertinent to your work. What are we talking about with liquid marbles?
So in this case, we have drops of liquid that they are encapsulated by nano or microparticles. And in this case, the particles, they don't have much favorable interactions with a liquid. So, for example, if you want to make a water liquid marble, you can take a sessile drop of water, and then you can coat it with hydrophobic particles, for example, Teflon microparticles. What you will end up with is a peculiar little object, as I like to call them, because they have interesting properties. For example, you will realize that this drop, the liquid marble, behaves as a non-stick drop, so it can easily roll on solid surfaces, for example, which is something that you cannot usually do with drops. They tend to stick on surfaces. At the same time, these liquid marbles, they behave like soft objects. So you can, if you apply gentle pressure on them, you will see that they have a soft character. On the other hand, if you press too much, so you apply very strong force, what you may do is to rupture this particle coating that I was talking about a second ago. So, and what will happen, the liquid will flow out of the marble. So you still realize that it looks like a soft object, but at the end it's a liquid object, if I may say. And these are interesting objects because, they also exist in nature. So, for example, there are some insects that they use them as efficient transport media to get rid of their own excrement, for example. And also it's interesting for different applications, as we'll discuss, I guess, in a second.
Yeah, so to recap a little bit, structural colors are displayed by a surface when the structural elements of a transparent material that selectively reflects a range of distinct wavelengths upon white light illumination. And that doesn't happen only in laboratory settings. And you've talked about that a little bit. Where do we see this taking place in nature?
Perhaps, let's say, the simplest optical process that can give rise to structural color is thin film interference. And in this case, we have a thin film of a given material, and we have reflection of waves from the top and the bottom surface of that film. And then these waves, they can interfere, and depending on the way they interfere, we will see different colors. This is, for example, we know from our everyday life with soap bubbles that they exhibit brilliant colors. But except of soap bubbles, this is a common way that nature uses to color some animals or insects, for example. So you can find that in wasps and flies. Of course, in this case, we don't have a soap film, but we have different materials, usually biopolymers like chitin. Apart from that, because that's the simplest mechanism that I described, nature uses creates some very elaborate, if I would say, nanostructures that they can interact with light and produce structural color. We see this frequently in birds. For example, we all know peacocks. They have these brilliant colors that actually they had captured the attention of Newton and Hooke already, records of that. But also we see it in pigeons, in ducks. We see in other insects, apart from the ones I mentioned before, like butterflies, wasps, moths, and beetles. And besides the animal kingdom, of course, we see that in the plant kingdom. So there are many plants that they use structural colors to color their leaves or fruit. There are some berries that they have this very intense blue metallic-like color. And actually, this is quite interesting for us because it's a similar phenomenon to what we have in the marbles that you described before. Again, we have the cholesteric self-assembly of the building blocks that interact with light and give these beautiful, vivid colors.
Manos Anyfantakis from the University of Luxembourg with us on All Things Photonics. Getting into the physics of your work, let's take a step back. The system we introduced in our intro and that you've spoken about here involves taking a common commercial polymer that is derived from cellulose and then demonstrating a new method for inducing that polymer's liquid crystalline self-assembly into, as you say, a cholesteric phase. This all took place with the periodicity needed to show structural coloring. And so the process, as we note, took place in an aqueous solution. You can describe this process better than I can. Tell me about the process that ultimately made the research successful.
So, as you said, we use a cellulose-based polymer. Actually, it's called hydroxypropyl cellulose, and this is something that's widely used in industry for many reasons. For example, in food applications, but also as an excipient in pills, for example. So, I think for about 35 years or more, it's known that when you dissolve this polymer or other cellulose-based polymers in water, above a certain concentration of polymer concentration, you will start seeing these structural colors. The reason for that, as you mentioned, is cholesteric liquid crystalline self-assembly of the building blocks, in this case the polymers. And what happens here is that these polymers, they have anisotropic segments. So they have, let's say, in a similar way, rod-like building blocks. So what happens when you increase the concentrations, these building blocks, they can adopt a parallel orientation to a common axis. This we call it a director in liquid crystal science. And locally we have what we call a nematic order. So now, because cellulose and cellulose-based materials, they have chiral interactions between the building blocks, this director that I described before undergoes a helical modulation along a single axis, and then it forms like a helix. So the distance now along the helix over which the director performs a full rotation, so a 360 degrees rotation, it's called the cholesteric pitch. When the pitch value is reduced to submicrometer values, so similar to the wavelength of white light, then if we illuminate the material with white light, only some wavelengths are selectively refracted, and that's why we see the color. So in other words, the pitch here represents the optical periodicity in the material, and this is the case because the building blocks are birefringent. Now, as I said, this was known for hydroxypropyl cellulose in water, but the practical problem there is that this process takes place above about 60 weight percent of polymer, and especially to have single colors. And if you try to do it yourself, so if you play a little bit with the material and you go at such high concentration, you have a lot of problems of handling the material because it's very highly viscoelastic. So if I would use simple terms, it looks like a kind of elastic paste. So it's very hard to manipulate that, of course. What we did was to use lower concentrations than the one I mentioned before, and we make drops of these solutions at lower concentrations. We encapsulated them with hydrophobic nanoparticles. We use silica particles in this case, and we made liquid marbles. As I explained earlier, it's easy to manipulate liquid marbles, so we just then pick up these liquid marbles and we can immerse them in an organic liquid which has finite miscibility with water. And then by adjusting the volume of this organic liquid, we can extract the desired amount of water from the marble, and then we can reach a final polymer concentration. Now the cholesteric pitch that I described before, we know that it's a function of this polymer concentration. So by adjusting the final concentration, we can program the pitch of the liquid marble, and of course then in turn we can tailor the structural colors of the liquid marble. Now I think this is a straightforward and reproducible way to prepare macroscopic, yet miniature, self-standing soft photonic elements using a sustainable material, nanomaterial like hydroxypropyl cellulose. And all this happened in a straightforward way, which is very, very reproducible, nevertheless. So we have very good control over the process.
And with the advance that you've established and outlined for us here, I believe you established a path for liquid marbles to synthesize cost-effective and also environmentally sustainable sensors. And that bit's important. With regards to possibilities in biobased sensing, what applications are you seeing as forthcoming?
So what we have seen from our research already is that our liquid marbles, which are based on a biomaterial, on a bio-derived material in this case, which is fully sustainable as you said before, they respond to application of different external stimuli with color changes that can be easily seen. So they are macroscopic color changes. For example, what we have done, we have changed the temperature of the liquid marbles, and we have seen that when we increase the temperature, the wavelengths that they are selectively reflected, they go to longer values compared to the equilibrium case. So, for example, if we have a green marble at room temperature, when we heat it, the color will undergo a red shift, so go towards the red spectrum of the visible light. Of course, this happens the other way around, so when we cool down the marbles, we observe a blue shift of the wavelengths of the reflected light. So, of course, this gives already the possibility to use them as a temperature sensor. And I have to mention that all these changes are reproducible. That's why it would be interesting. Apart from that, we also try to combat our liquid marbles, and we have seen that also the application of pressure gives rise to color changes that they can be seen by the naked eye. So, of course, this would give the possibility to use them as pressure sensors, for example. And another last thing, which I think is perhaps the most important, we also expose our liquid marbles to toxic chemicals. In this case, we use methanol. This is a toxic organic solvent that is used a lot in the industry. And what we have seen when we expose the marble to methanol, again, we observe color change that we can see easily by the naked eye. So I think this can be in the context of sensing volatile organic components, which is a big thing currently in the industry. I think our marbles, except of methanol that I mentioned before, they could possibly sense other dangerous chemicals, for example, tetrahydrofuran or even chloroform, for example. But of course, this we have to see in the future. Apart from these sensing applications, I think what else could be interesting, we demonstrated that our liquid marbles, when we irradiate them with a parallel white beam, and then we look at different angles, so the light scattered at different angles, we see that we can split the light. So we get back, depending on the angle, we get light of different wavelengths. So this, in combination with the fact that we know that the optical response is very sensitive to temperature, it could give us the possibility to make like spectral splitters that could be controlled by temperature. So I think that's another interesting possibility in terms of photonics now and not sensing.
Manos Anyfantakis is from the University of Luxembourg's Experimental Soft Matter Physics Group, part of the university's Department of Physics and Material Science. Thank you for being on with us.
Thank you very much, and I was happy that you were interested in our research, and it was a pleasure to discuss with you about this.
That does it for this episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to Joel Williams with the news. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website. Subscribe, never miss an episode. I'm Jake Saltzman. This has been a Photonics Media production.